Alrighty, we're back again, and this time we have something very new. I was just taking a look at the quantum computation repo where I hold basically all of the code for these videos, and I realized, wow, it's been like 2 months, almost exactly, just under 2 months, since I actually wrote any code in that repo or did any videos that had code in that repository. So I have a lot of ideas, don't worry. A lot of them also include some classical machine learning, but I have a lot of things hopefully coming together. So more TFQ is on the way. I can say that. I don't know how much you should believe me since I think I say that every video, but nonetheless, perhaps this time it will be true. I do have a lot of good ideas. I've just been working hard on a lot of different things. So anyway, in this video, we're going to be talking about something new, as I said, not just new to the channel, not just new to me talking about it, but truly new in the sense that it's a package that just got made public, I believe. I don't know exactly when. Maybe let's see, the first release, beta release came out 16 days ago. So, brand new quantum package, and that package is called OpenQAOA. So, of course, I'll link it, the package in the description. And they also have a Discord, which I'll directly link to in the description. It's in open beta right now, so, just be aware of that. But it's a package put out by Entropica Labs. Let's see, let me make sure that, yeah, that's, I just making sure it's labs and not something else. And so, yeah, it's just a new package. I was part of the closed beta, actually. That's why I'm sort of involved in it. I don't just peruse, GitHub looking for brand new repositories to check out, but I think it's worth investigating. If you go to the GitHub page, you'll notice I've already been somewhat involved. I've not contributed at all, but there's a lot of issues that I've raised when I was experimenting with it, and there might be more issues that I'm going to raise. And so, yeah, basically what this video is going to look like is I'm going to give a brief sort of example rundown of some code using OpenQAOA. I'm going to sort of give a gist of my impression of it, and then I'm going to actually give some review and feedback at the end of the package. I mean, maybe I should just email, the people who made this with my feedback, but I'll just make a video about it instead. So the first thing we're going to do is sort of go through a code example, but at a high level, I should probably say, what the hell is this? Well, I don't know, it should be somewhat self-explanatory. OpenQAOA is a package that, that is focused on QAOA, the quantum approximate optimization algorithm, and it strives to improve the ease and quality of research in that direction. And so it's sort of consolidating across backends, across different ideas, across problem sets, trying to sort of consolidate this into a useful package that people interested in QAOA research and applications can evaluate. How much it succeeds in that regard, we will talk about at the end. And not that I'm going to criticize it in any way. It's in any mean way. It's an open beta. I recognize that's one of the biggest benefits that I'll also talk about at the end, is that there's a lot of flexibility. So yeah, we'll get right into it. So QAOA, if you haven't, don't know anything about QAOA, I've done like 3 or 4 videos on it already, maybe only 2, but there's plenty of stuff that you can peruse my channel for. So yeah, in this one, this is sort of a simple example. This just shows some of the basic ideas. We're going to check out basically the relative difficulty of a selection of problems. So everyone always does QAOA on MaxCut, right? But and MaxCut is obviously a very challenging problem. It's MP. It's an MP hard, if I remember correctly. And so are all of these other sort of combinatorial optimization problems. And you can actually rearrange them to you can reduce them to each other. I think independent set is a really common one to reduce things to, but it's been a while since I did NP reductions. So yeah, so in terms of complexity theory, all of these problems are the same comparable class. But in practice, right, that's not always the case, that all problems are of the same difficulty. For example, all problems in P are very much not the same. Constant time and n to the 5 billion, order of n to the 5 billion are both in P, but that doesn't mean you don't want constant time algorithms. So yeah, looking at this going forward, what we're trying to do is say how hard actually are some set of problems to QAOA to solve sort of empirically. This is not really super rigorous. This is just an outline of a project. If people are interested in continuing this project, I can talk about that as well. I'm trying to get around to making a website. Maybe by December I'll do it. And one of those sections will be open projects that people can collaborate on, and this will probably be one of them. So anyway, we have the problems here that we're importing. They have these handy problem classes for us. And then we have our tools, the recursive QAOA and the normal QAOA, and then we have our sort of exact solver. So what we're going to be doing here is iterating through 2 to 15 qubits and basically generating these problems, random problems for 3 repetitions, solving them using QAOA, and then taking the absolute value of the energy difference and evaluating that for a set of problems. So the first set of problems we're doing are min vertex cover, number partition, and maximum cut. You might be looking, why do I import all of these and why do I have all of these? Because originally there was more to this, but I pared it down to work with current, main branches and everything, and to be fast. So it's pretty straightforward. This is all just Python code. So we instantiate our QAOA object. We specify our minimum vertex cover and that we want a random instance of this size for the number of nodes with that edge probability of existing. And then we get our quantum unconstrained binary optimization problem from it. We find the ground state by putting in the problem Hamiltonian. We compile the problem and then we optimize it. And then we save the results. You can see it's pretty straightforward to use. Then we do the exact same thing with our QAOA. So you can see I'm just getting into the very basics of it here. There's a lot more flexibility that if you go through their documentation, you'll find. But this is sort of more, I guess, the practitioner, right? Where you don't want to think about all the nitty-gritty details. This is sort of the most bare bones walkthrough that you can do. And so when we do all this, we see here I'm doing a log plot of it. We can see QAOA versus RQAOA. We can see that RQAOA can basically exactly solve it up to some problem size, after which it has a sort of constant error rate. You can see this isn't increasing much, whereas QAOA sort of increases on number partition, especially quasi logarithmically or exponentially here, I guess, because this is 10 to the first to 10 to the third. So this is just an interesting, I think if you flush this out a lot more, you could have interesting results, but this is just sort of the bare bones of it. So this is not by any means a just or a comprehensive review of the package. This is just saying, hey, look, this is the workflow that you're probably going to be using. You might not be using random problems though. You can obviously create problems using whatever specific graphs you want. And there's a lot of flexibility in compiling and optimizing them that I recommend you check out the package for. This is just sort of the introductory video letting people know that this package exists. I'm not like